Usually when we think of clinical medicine, we picture sterile laboratories and, stainless steel vats. We expect our medical treatments to be manufactured with just absolute binary precision. You take a pill and you know exactly what is in it because a team of chemists engineered it that way in a completely isolated room.
Right, yeah, we really like to cling to that illusion of the sterile laboratory.
Oh, absolutely. But when you step into the world of advanced wound care, you suddenly find yourself looking at a medical product that is manufactured by wild insects flying around a rugged, wind-blown mountainside.
It is fascinating because, well, we like to think humanity completely controls the manufacturing process of every medicine we use. But in this specific case, the Earth itself is the laboratory. The manufacturing floor is literally a volcano, and the technicians are plants and bees.
I am so glad we are getting into this today. For those of you listening, I am your host, and by day, I am a professional, large-scale commercial beekeeper operating up in North Dakota. I manage thousands of colonies strictly for honey production and commercial pollination.
Which is an incredible scale of operation, honestly.
Yeah, it definitely keeps me busy. My days are spent elbow deep in the real-world mechanics of the apiary. I am talking about the gritty details like queen breeding, managing the flight patterns of foragers, and utilizing pollen sub to keep my colonies robust through some pretty harsh Midwestern winters.
Right, you're dealing with the practical survival of the hive.
Exactly. And because of that heavy field background, I have a very strong skepticism toward industry fluff. I mean, I really do not care about marketing buzzwords. I need to know what actually works in the dirt and inside the hive.
That is exactly why I'm here, to provide the academic perspective to balance out all that practical field experience. My background is in apiology and melitology, which, for those who might not know, are the scientific studies of honeybees and wild bees.
So you look at the tiny details while I look at the whole field.
Pretty much, yeah. Instead of managing thousands of hives for commercial output, I spend my time exploring the fascinating intersection of physics, biology, and phytochemistry. I look at the microscopic and environmental factors that explain the exact how and why behind bee behavior, and of course the highly complex chemistry of the plants they visit.
Together, we are taking you on a very specific mission today to explore MGO terroir mapping. And before we really get into the weeds here, I want to mention that you can find the complete MGO terroir mapping at Manuka and Wound Science. You just visit manukawoundscience.org.
It is an incredible resource for anyone wanting to visualize this stuff.
It really is. And to put this mapping concept into everyday language for you, MGO terroir mapping is basically a geographical blueprint. It is a map that shows exactly how the soil and the climate of a specific region dictate the medicinal potency of honey long before the bees even leave the hive.
A geographical blueprint is actually the perfect framework for this. It sets up an incredible foundation for understanding how the Earth itself essentially manufactures medicine.
Because it doesn't just start with the bees, right?
No, not at all. The medicinal power of this specific honey does not come from the hive alone, and it definitely does not come from the bees themselves. It starts purely, fundamentally in the soil.
See, when I think of honey production, my eyes are almost always looking up. I am looking at the weather systems moving in, or I'm looking at the bloom on the trees, and I am watching the flight paths of my foragers to see where they are heading.
Right. You are looking at the immediate environment.
Yeah, but you were saying we need to look down at the literal dirt.
We have to look all the way down to the geological source.
Okay.
Before the active antibacterial compound, which is methylglycol or MgO, before that ever forms in a jar of honey, it exists as a precursor chemical called dihydroxyacetone.
Okay, that is a mouthful. Let us just stick to DHA for short.
Yeah, DHA is much easier. So this DHA is found naturally in the nectar of the Leptospermum scoparium plant. Most people are going to call that the Manuka bush. But here is the critical part. The concentration of that DHA in the flower depends entirely on what the plant is actively pulling up through its root system.
So the dirt dictates the chemistry of the nectar. What exactly is the plant looking for down there in the ground?
Volcanic minerals are the key players here. We are looking really closely at heavy elemental minerals like manganese and iron.
Really? Iron and manganese in the dirt change the flower nectar.
Absolutely. These elements act as essential components that dramatically boost the DHA concentration in the nectar. Manganese, for instance, acts as a cofactor in the plant's enzymatic pathways.
A cofactor, like a catalyst.
Basically, yes. Think of a cofactor like a biological spark plug. Without that specific mineral spark, the plant's internal machinery just cannot synthesize DHA efficiently. So you can have two Manuka bushes with the exact same genetics, but if they're growing in different soil chemistries, the nectar they produce will be completely different on a molecular level.
Wow, okay, that makes sense from a botanical standpoint. But soil pH has to play a vital role there too, right? Because in any type of farming or agriculture, the pH level of the soil dictates whether those elemental nutrients are actually unlocked and available for the root system to absorb.
You hit the nail on the head. Acidic soils with a pH sitting strictly between 4.5 and 5.5 create the absolute perfect conditions for synthesizing these compounds.
That is pretty specific.
It is very specific. That exact acidic sweet spot dissolves the minerals just right, and it correlates directly with a massive spike in the production of bioactive compounds in the flowers.
Wait, from a practical beekeeping standpoint, this does not fully track for me yet. I mean, I understand that acidic, mineral-rich soil provides the chemical building blocks, but soil chemistry is basically stationary. It just sits there in the ground.
Right, the soil doesn't move.
Yeah. So if I plant two genetically identical seeds in different soil, sure, they get different nutrients. But why would one suddenly decide to ramp up chemical production? What is the actual evolutionary trigger that makes the plant work harder to produce these compounds?
That is a great question. The answer lies in environmental stress factors. The plant is not just sitting passively in the soil soaking up minerals. It is constantly reacting to threats in its environment.
Threats like weather.
Exactly. When we look at the specific geography of New Zealand where this medicinal honey is produced, altitude plays a massive role. The ideal altitude band between 200 and 600 meters creates significant daily temperature fluctuations.
So it is getting hot during the day and freezing at night.
Precisely. It gets quite warm during the day and very cold at night. Those drastic temperature swings trigger a biological survival stress response in the plant.
So the plant genuinely feels threatened by the shifting climate and goes into full defense mode.
Yes, and this stress response is compounded by rainfall. The ideal zones get an optimal annual rainfall of 1,200 to 1,500 millimeters.
That sounds like a very delicate balance.
It really is. That highly specific amount of rainfall provides just enough moisture to keep the plant alive, but it prevents the nectar concentration from getting diluted. And it also prevents the root zones from getting waterlogged, which would just rot the plant.
Oh, I see.
Yeah, so to protect itself from the combined environmental pressures of altitude, temperature swings, and specific hydration levels, the plant actively increases its production of beneficial phenolic compounds. It is basically shielding its own cells.
You know, it makes me think of a high-end vineyard. A grapevine produces much better, significantly more complex wine grapes when it has to struggle in rocky earth and harsh weather conditions.
That is a brilliant analogy, actually.
Thanks. I mean, the roots have to dig deeper, the plant has to fight for survival, and the resulting fruit is dense with flavor and chemicals. If you pamper a grapevine in perfect, easy soil with gentle weather, the resulting wine is incredibly boring and watery.
Exactly. Just like that grapevine, the Manuka bush produces a much more potent medicinal nectar when it faces the targeted, localized stresses of high altitude and volcanic soil.
The botanical struggle is exactly what creates the clinical value. The plant manufactures these dense chemical compounds as a localized defense mechanism just to survive the harsh terrain. And my bees, well, the bees are simply flying in and harvesting the chemical results of that botanical stress.
Exactly right.
So if we connect these to the bigger picture, these environmental stresses obviously are not evenly distributed across a whole country. They must map out across different geographic regions of New Zealand in very distinct ways.
They absolutely do.
Let us map out those regional hotspots for the listener. Where are the true heavy hitters located on this geographical blueprint?
Well, the absolute heaviest hitter is the East Cape region. When you look at the East Cape, you have incredibly rich volcanic soils combined with harsh coastal microclimates that just batter the plants.
Sounds rough for the plants.
It is. Plus, there is very little agricultural interference from other commercial crops. These factors create the ultimate perfect storm for medicinal potency. The honey produced in the East Cape consistently hits MGO ranges from 550 to over 850 milligrams per kilogram.
Wow. Over 850 milligrams per kilogram is a staggering concentration.
In the radical community, that is the undisputed gold standard for clinical grade potency.
But, you know, from a commercial production standpoint, a rugged, harsh coastal area probably does not yield the highest volume of barrels. I know from experience bees do not like flying in terrible coastal winds. So what about the areas doing the heavy lifting for commercial volume?
For larger commercial volumes, the industry looks at the Northland and Coromandel Peninsula regions. Northland offers warmer overall temperatures and a much more extended flowering season.
Ah, so the bees have more time to work.
Exactly. That warmer, gentler climate allows the bees to fly longer and gather significantly larger harvests. But the trade-off is real. Because the plants are less stressed by the weather, the MgO levels are moderate to high, typically sitting between 300 and 500.
Still very respectable for general consumer use, but obviously not hitting that 850 clinical ceiling of the East Cape. What about the Coromandel area?
Coromandel is fascinating because it features drastically varying microclimates along its hillsides. You have hillside hives capturing completely different environmental pockets within a very small radius.
Like literally on the same hill.
Yes, one side of a hill might face the harsh coastal wind, while the other side sits in a sun-baked valley. Because of that extreme local variation, the honey there yields MgO levels spanning a very wide range, anywhere from 400 to over 600, depending on exactly where the hive was placed.
Okay, so warmer weather gives you commercial volume. Rugged coastal volcanic hills give you peak clinical potency. What happens when you go much further south, like down to the bottom of the island where it gets genuinely cold?
If we look at Southland and Otago, the entire dynamic shifts. They have very healthy leptospermum populations and different but still highly fertile soil compositions. However, the much cooler temperatures in those southern regions physically reduce the plant's biological ability to synthesize DHA.
Because it is just too cold for the chemistry to work.
Right. The enzymatic pathways we talked about earlier just slow down in the cold.
Right.
So despite having healthy, blooming plants and eager bees, the resulting honey has much lower MgO levels, usually falling between 100 and 250.
See, my apiary brain just explodes thinking about that. I could have an apiary set up in Otago with perfectly managed foragers. I could completely eliminate drifting.
Drifting is when the bees go to the wrong hive, right?
Yeah, drifting is when bees get confused and enter the wrong hives, which really reduces your specific crop yield. So I could fix that. I could be running the tightest, most professional pollination operation in the world with incredibly strong queens. Yet my harvest would still fall completely short of clinical grade potency simply because the regional temperature cap limits the chemical ceiling of the harvest.
It is entirely out of your hands.
It is. The environment places a hard mathematical limit on my product before my bees even touch the flower.
You simply cannot outmanage the geographic blueprint. No amount of beekeeping skill changes the temperature of the dirt. And, this brings us to a crucial biochemical transition.
How so?
Well, since the regional breakdown establishes that the plants are producing DHA in their nectar rather than MgO, we need to trace how that precursor actually transforms into the final potent product in the jar.
Right. So if the plant is only producing DHA in the dirt, but the medical-grade honey requires MgO to treat wounds, there is an obvious missing link here. What exactly happens between the flower and the jar?
It is a fascinating process.
I like to call this the from nectar to numbers transition. Because when my foragers first bring that raw nectar back to the hive, the numbers look absolutely terrible from a medical standpoint. When you test a fresh harvest straight out of the comb, it is incredibly low in MgO, maybe sitting at 50 to 100 milligrams. But it is massively high in DHA, sometimes testing at 500 to 800 milligrams.
The biochemistry behind that shift is remarkable. The conversion from DHA into MgO is entirely a non-enzymatic chemical reaction.
Meaning the bees are not doing it.
Correct. It is not driven by the bees adding digestive enzymes from their honey stomachs, which is how most standard table honey cures and ripens. Instead, it is a slow, steady chemical transformation that happens during storage in a warehouse. It is entirely dependent on time and temperature.
And the timeline for that maturation process is incredibly strict. You do not just put a barrel of fresh honey in a dark warehouse and hope for the best a year later. It takes 3 to 6 months of storage at highly specific temperatures.
Very specific.
We are talking exactly 20 to 25 degrees Celsius, maintained constantly. Under those exact thermal conditions, the DHA slowly depletes and converts chemically into its peak MgO potency. When it finally hits that peak, the DHA drops down to maybe 100 or 200, and the MgO maximizes at 400 to 800 plus.
Exactly. The controlled warmth of the maturation facility accelerates those non-enzymatic chemical reactions. The DHA drops, and the MgO rises proportionally in an almost perfect inverse relationship.
It reminds me of traditional old-school photography. Think about a raw photograph negative. When you click the shutter on a camera, the image is captured there on the film, but you cannot actually see it yet. It was completely useless in that raw state.
Right, you have to develop it.
Exactly. That raw negative has to be carefully taken into a darkroom and developed over time. You have to use specific liquid chemicals and controlled lighting conditions to slowly reveal the final, highly valuable image. Fresh Manuka honey is that raw negative. The climate-controlled maturation room is the dark room.
I love that comparison. But there is a vital caveat to that darkroom process we have to acknowledge. The regional terroir absolutely determines the final MgO ceiling.
Meaning you cannot create what is not there.
Precisely. You can have the most expensive, perfectly temperature-controlled storage facility in the world. But if the volcanic soil did not initially provide the plant with the raw minerals to produce high levels of DHA, well, no amount of perfect warehouse storage can create MgO potency out of thin air. The Earth dictates the maximum potential. The storage facility simply actualizes it.
So we have spent all this time explaining the complex maturation process and how we achieve these massive MgO numbers. But why does hitting those specific high numbers actually matter when you walk into a hospital setting?
This raises a critical point about the broader chemical profile of the honey. MgO gets all the headline attention because it acts aggressively. It physically attacks bacterial cell walls and destroys them, making it highly antimicrobial.
Right, it kills the bad stuff.
Yes, but phenolic compounds actually carry massive, often under-discussed weight in clinical applications. Two specific phenolic acids really stand out here. First is caffeic acid. This compound actively reduces oxidative stress in the wound bed. More importantly, it heavily supports fibroblast migration.
Fibroblasts, what are those exactly?
Fibroblasts are essentially the cellular architects of the human body. They need to migrate into the damaged wound area to lay down the structural framework for new tissue.
Got it. And what about the second phenolic compound?
That is ferulic acid. Once those new cells are forming, ferulic acid protects them against UV-induced damage and actively enhances collagen synthesis in the healing tissue. Both caffeic and ferulic acid are highly concentrated in honey that comes directly from iron-rich volcanic soils.
I have to ask a crucial practical question here. Do these phenolic compounds just happen to exist alongside the MgO by evolutionary coincidence, or do they actually work together in a functional, mechanical way inside a human wound?
Oh, they provide deeply synergistic wound healing. They absolutely work together as a cohesive unit. The MgO acts as the primary antibacterial agent. It is the bulldozer.
The bulldozer, I like that.
It goes in, clears out the active infection, and breaks down stubborn bacterial biofilms.
Biofilms, those are the slimy shields, right?
Exactly. Biofilms are basically slimy protective shields that bacteria build to defend themselves against standard liquid antibiotics. MgO shreds right through those shields. Meanwhile, the phenolic acids are the construction crew coming in behind the bulldozer.
Oh.
Yeah, they actively promote tissue granulation, which is that fresh, bumpy, red connective tissue you see forming at the very bottom of a healing wound. And this entire synergistic matrix of clearing and rebuilding is anchored by a highly unique compound called leptospirin.
That dual action mechanism is incredible. You have the bulldozer and the construction crew working together. It perfectly explains why the specific natural product consistently outperforms synthetic, lab-made MgO solutions in medical trials.
It really does.
Because you cannot just synthesize MgO in a test tube, apply it to a wound, and expect the same healing results. Because if you do that, you are missing the construction crew. You are missing the caffeic acid, the ferulic acid, and the leptospirin that actually rebuild the skin.
Exactly. The modern laboratory can easily replicate the bulldozer, but it cannot replicate the complex botanical construction crew that the volcanic soil originally provided to the plant.
Because this dual-action medical product is so highly valued in hospitals and burn wards, it naturally commands a massive premium on the commercial market. And anytime you have a premium agricultural product selling for high prices, you inevitably have bad actors trying to cheat the system to make a quick buck.
Unfortunately, yes. It is a huge problem.
The medical industry relies on this stuff to save limbs and treat severe burns. So how does the industry actually protect the harvest and prove exactly where a jar of medical honey really came from?
The industry relies on a highly advanced analytical method called geographical fingerprinting. Standard laboratory tests just tell you the MgO potency number. But unfortunately, that number can be easily faked by a counterfeiter who buys cheap, low-grade clover honey and simply stirs in synthetic MgO powder.
Which is terrifying for patient care.
It is. So to combat this, authenticators use mass spectrometry and mineral profiling. They analyze the trace elements in honey down to parts per billion.
Parts per billion. Just to visualize that scale for you listening, measuring parts per billion is like finding one specific microscopic drop of water inside an entire Olympic-sized swimming pool. That is an insane level of microscopic detail.
It is entirely necessary to catch the fraud, though. Every geographic pocket of soil has a distinct elemental signature. We also use isotope analysis. This specifically looks at the carbon-13 to carbon-12 ratios within the honey matrix.
What do the carbon ratios tell us?
These specific carbon isotopic ratios reflect the regional water supplies and the specific photosynthetic pathways of the plants reacting to that exact microclimate. When a plant experiences different water stress, its stomata behave differently, locking in a specific carbon signature.
That is wild.
It creates a completely unique microscopic isotopic fingerprint that is literally impossible to replicate in a laboratory setting.
The commercial reality of this is staggering. Because the medical-grade honey commands such a high price, counterfeiters constantly try to blend genuine product with cheaper alternatives or synthetic additives to stretch their profit margins. A standard hospital lab test might look at a forged batch, see a high MGO number, and give it a false pass.
Right, if they only look at the MGO.
But it is completely impossible for those counterfeiters to fake the complex mineral signature, the specific isotope ratios, and the localized phenolic profile of a geographic region. It makes me think of trying to forge a masterpiece painting.
How so?
Well, a criminal might get the colors right. They might even perfectly copy the famous brushstrokes of the original artist. But the moment an art expert runs a chemical analysis on the canvas fibers and tests the true age of the paint pigments, the fraud is instantly revealed. You just cannot fake the fundamental chemistry of origin.
That is a perfect way to look at it. The geographical fingerprinting catches the manipulations every single time because you simply cannot forge the complete holistic chemical signature of a specific plot of volcanic earth in New Zealand. The soil leaves an indelible mark on the nectar.
I want to summarize the incredible journey we have just mapped out together today. We have followed a truly amazing path from a stationary volcanic mineral deposit up through the roots of a stressed plant sitting on a harsh hillside, into the stomach of a foraging bee, through a highly controlled temperature darkroom in a warehouse, all the way to a verified clinical wound care product in a hospital.
It's quite a journey.
It really is. And for me, as someone who manages thousands of commercial colonies day in and day out, this is a very humbling reminder. True apiary value goes far beyond just keeping our colonies alive and healthy. It requires a deep, fundamental understanding of how the earth itself programs the harvest before a single bee ever takes flight.
And from the clinical side, it emphasizes exactly why medical professionals and hospital administrators must demand complete certificates of analysis in their medical procurement. It is not enough to just look at an MGO number on a label anymore. You need to verify the leptosprin levels, the phenolic profiles, and the complete mineral analysis.
Because that proves it is real.
Exactly. Ensuring that absolute transparency in sourcing directly translates to actual, reliable clinical efficacy for patients suffering from severe, life-threatening wounds.
We want to leave you, our listener, with a final thought to ponder as you go about your day. We have talked entirely about how specific altitude bands, temperatures, and rainfall create the perfect botanical stress for these plants to produce high-grade medicine.
That's the geographical blueprint.
Right. Well, I want you to consider this. How might shifting global climate patterns and changing annual rainfall eventually alter these highly specific altitude and temperature zones? If the weather changes, the botanical stress changes with it. We might eventually be forced by the shifting global climate to entirely redraw the geographical blueprints of where the world's most potent natural medicines can be cultivated.